Good morning, everyone. I'm Wangze from Shanghai Jiao University of China. The title of my report is Universal Data Acquisition System for Flexible and MEMS-based gas sensors. My report is organized into the following 5 sections. Our research team has been focusing on the research and application of advanced gas sensors for more than 10 years. Among many types of gas sensors, chemical resistance type, also known as semiconductor gas sensor, is a type of most widely used gas sensors. Semiconductor gas sensors, especially those based on MEMS technology and non-functional materials, usually have large initial resistance and extremely high sensitivity. The application of machine learning and fully automatic experimental devices have put forward stricter requirements on front-end conditioning circuit of gas sensors. The former requires the acquisition circuit to have high precision and range, while the latter requires that the circuit must be able to automatically controlled by the software. The main part of the whole system is divided into 3 modules, including the heating module, the temperature collection module, and the resistance acquisition module. The heater heats the material of the gas sensors to a certain temperature, while the temperature collection module detects the real-time temperature of the sensitive material. The resistance of a material changes drastically with its temperature, and the resistance acquisition module can realize high-precision, wide-range measurement of resistance. The photos of the 3 modules are shown below. Many modules are also attached to the system, including the microcontrol unit, the inter-circuit board cascade, and the wireless communication. As the central control unit of the system, the MCU is able to control the 3 main parts of the system. The RS-485 protocol is employed to achieve the cascade of different boards. So many boards can be tested simultaneously. The system can construct the communication with host computer software. The schematic of the system, the photo of the circuit realizing the RS-485 and the Modbus modules are shown below. In the heating module, the PWM wave is generated by the MCU and is modulated by a second-order low-pass filter to an approximate direct current voltage. The DC voltage is employed to heat the gas-sensitive material. To change the heating power of the heater, the duty cycle of the PWM wave is modulated by the MCU. The higher the duty cycle, the higher the output power. The schematic diagram of the heating module is shown below. In the heating module, two modes can be selected, including the PID control and the direct power control. As for the sensitive material coated on the flexible finger electrodes, the PID algorithm ensures the stability of its temperature. The direct power control is applied to the MEMS gas sensor arrays, and the heating power can be regulated on the upper computer software. The photo on the left shows the MEMS and the flexible gas sensor arrays. The photo of the whole system with MEMS and the flexible gas sensors is shown in the middle. The effect of the PID and the direct power control is on the right. In the temperature collection module, the thermistor PD100 is employed to detect the temperature change of the material. A constant current source is implemented in the circuit, and the resistance change can be converted to the voltage change. Then the analog voltage signal is transmitted to the differential amplifier circuit and connected to the ADC of the MCU. In this way, the voltage signal can be converted to a digital value, which corresponding to the temperature of the material. The schematic diagram of the temperature collection module, the performance of the heating and the temperature collection module is shown below. The resistance acquisition module is the core component of the whole system, and the normal multi-module and the reconstruction conditioning circuit is employed to match the resistance of the material. In this work, the constant voltage drive mode is implemented, and as shown in the schematic diagram below, the resistance can be expressed as the equation. In this work, the UA is fixed, and the Rx is dynamically changed according to the voltage output U out. The next is a more detailed description of the resistance acquisition module. The multi-module self-reconstruction front-end conditioning circuit is designed to achieve high precision and a wide arrangement of resistance. This circuit is mainly composed of 4 modules: the operational amplifier connection module, the resistance selection unit, the measurement drive unit, and the signal conversion unit. It has 2 main characteristics. The first one is multi-module. It can perform constant voltage measurement, constant current measurement, electrochemical measurement, and parameter calibration in one circuit. The second is self-reconstruction. The function conversion is all controlled by the multiplexers, which are performed according to the software instructions. The block diagram of the fully functional circuit is demonstrated in the left. It mainly includes an amplifier connection unit, 2 resistance selection units, a measurement drive unit, and a signal conversion unit. By setting the control ports F0, F1, and F2, changing the position of the sensor pin port, the circuit can achieve different functions. By adjusting the value of G1, G2, G3, and G4, 2 independent resistance selection units can be set with different load values to dynamically adjust the gain and measurement range during the test. The figure shows the equivalent circuit in different operation modes. In figure A and C, the amplifier on the left constitutes a programmable constant current source circuit, and the amplifier on the right constitutes a programmable reserve amplifier circuit. In figure D, the left amplifier constitutes a potential static circuit, and the right amplifier performs a transimpedance amplification. By adjusting the level of F0 to F2, functions such as constant voltage measurement, constant current measurement, circuit calibration, and electrochemical measurement can be realized. In this work, the constant voltage measurement is employed to match the resistance value of the material. The measurement circuit can automatically switch the range under the control of the firmware and track the change of resistance in real time. Through the staggered design of upshift and downshift, the stability of the shifting process can be greatly improved. These 6 figures shows actual measurements of the application circuit using standard resistors in the range of 0.1 kilo to 100 kilo ohm. The resistance box is used for testing in the range greater than 100 kilo ohm. The discrete standard resistors are used for testing. The results show that the circuit can easily achieve dynamic measurement with a range of 7 orders of magnitude, with an average error less than 0.5%. In this study, a universal data acquisition system for flexible and MEMS-based gas sensor is designed, and the highlight of the system is that it is compatible with both the MEMS and flexible gas sensors. Combined with the heating module and the temperature collection module, pressure-temperature control can be achieved, like the PID temperature control for flexible gas sensors. The core component of the system is the novel multimodule and the self-reconstruction conditioning circuit, which can achieve ultra-wide range and extremely high precision measurement of resistance of gas-sensitive material. Meanwhile, the simultaneous measurement of gas sensor area can be achieved through the RS-485 protocol. This work proposes a method for heating, temperature collecting, and resistance acquisition, which demonstrates significant uniformity and adaptability across diverse sensing domains, emphasizing their broad application in sensing technology. I would like to express my gratitude to the staffs of our research team for their creative work. Some of our works are listed on the right.
Thank you for this presentation. Thank you.
Thank you very much.
So